A really quick summary of section 12.1 about some basic trig functions. So let's talk a little bit about right triangles because it's all about right triangles. Remember, right triangle has a 90-degree angle in it and then two angles that also sum up to 90 degrees. So we could label this guy up if we wanted here as a triangle A, B, C, and we always put the side length opposite the angle. So this would be side little c here, side little b, and side little a. So always opposite the angle, and that's kind of important, especially when we're doing Pythagorean theorem in a second here. All right, so Pythagorean theorem, you may remember this one. It says if you take the sum of the squares of the two sides is equal to the square of the longer side. So it's a formula we get to use. But some of these have names to them. This longer side we call the hypotenuse. You might remember that. And these we just call the legs or the sides. We'll just call them sides here. Two sides and a hypotenuse. So the sides are always going to be shorter than the hypotenuse. Hypotenuse is always going to be the longest leg. And it's always, always, always opposite the right angle. Okay, so that's some important pieces to just a basic right triangle. Okay, so this Pythagorean theorem can be useful if you have, say, a right triangle and you only know what two of the sides are and you want to find a third side. Well, you just plug them in here. This would be your A and B, and then you can find C. You just got to remember, if you were doing this particular problem here, for example, you'd say 2 squared plus 3 squared equals C squared. If you put these together, this is going to be 4 plus 9 equals c squared, or 13 equals c squared. To find c, the actual length, you're going to have to take the square root of both sides in order to do that. Okay, so on a lot of these, you can use your calculator and just round it off to the nearest tenth. All right, some other things that are important here, trig ratios. So now we're getting in the nitty-gritty of this. Trig ratios or trig functions, sine, cosine, tangent. You may have heard about those before. This is what they actually mean. If we have a right triangle and we consider some angle down here, we'll call this theta. Okay, that's the Greek letter theta. So it's pretty commonly used for angles in trigonometry. And from the standpoint of angle theta, well, first of all, this is our hypotenuse over here, right? Long side, opposite the right angle, always going to be our hypotenuse. But we need to name these other sides here. Okay, so from the standpoint of theta here, if you think about this side over here that is opposite that angle, well, we call that the opposite side. Okay, so this is our opposite side, and then the side that is adjacent to or right next to that angle, we call that our adjacent side. So opposite, adjacent, and hypotenuse. Okay. And that's kind of important. Now, keep in mind, if we said, oh, let's change where our angle is at, maybe we want to go from this angle up here. Now, this side would be opposite, and this side would be adjacent. So it's all relevant, or all relative to what angle you're going from. We only go from those two acute angles, never the right angle here, because it's always going to be opposite our hypotenuse. Okay. All right. So what are sine, cosine, and tangent? Well, they are defined as such. So this is really important that we're talking about really the definition of them here. So they're defined as following. So sine, if you take sine of this angle theta here, so we're going from this angle down here, theta. The sine of angle theta is defined as the ratio of the opposite side divided by the hypotenuse. And I'm going to start abbreviating these after this. In other words, the side lengths. So it's actually two numbers divided by each other. So it's a ratio of two side lengths. That's what it's defined as, okay? Cosine, we'll abbreviate that COS, cos. That's adjacent over hypotenuse. And tangent, or just tan, is opposite over adjacent. Okay, so that's what those are defined as. And so it literally means if I want to take the tangent of some angle and I know the side length, I literally just take the opposite side and divide it by the adjacent side. It's really that simple. It's really that simple here. Okay. Now there's a way to help us remember that though. If you look at the first letters here, S, O, H, C, A and H, T, O and A, it spells out so, ka, toa. So if you remember that little acronym there, you can remember that sine is opposite divided by hypotenuse, cosine, adjacent divided by hypotenuse, tangent, opposite divided by adjacent. And makes it easy to remember. Now we do have some reciprocal trig ratios as well that go along with sine, cosine, and tangent. So it turns out sine has a reciprocal trig ratio called cosecant, and we abbreviate that as CSC. And all it is really just the reciprocal. So like I said, these are the reciprocal trig ratios. It's the reciprocal of sine. So what's the reciprocal of sine? Well, it was opposite over hypotenuse. So now we're going to write it as hypotenuse divided by opposite. Reciprocal, remember we just flip the fractions when we do that. Multiplicative inverse, we call that. Cosine has a reciprocal that is secant, or we abbreviate that SEC, and that is hypotenuse over adjacent. And then tangent has cotangent, or COT, that goes along with it. And instead of opposite over adjacent, that's adjacent over opposite side. Okay, so we actually have 6 total trig ratios that we're dealing with. That's it, okay? Just 6 trig ratios, and all they do is it's pretty much all the possible combinations of how we can relate the sides of a right triangle to each other. All 3 sides, that's pretty much every possible combination we can do, okay? So, but this right here, SOHCAHTOA, super duper important for helping us to actually remember those. I usually tell kids to write that at the top of your page when they're working these problems, okay? So then we can do a little example here. Let's find the 6 trig ratios or functions for theta for the following right triangle. So here we have a right triangle that has 1, 2, and we have a missing side over here. And so we need to actually find that. So right now, from the standpoint of theta here, this is our adjacent side, right? If we look out, we see that's adjacent, and this side over here is our hypotenuse, okay? It's the long side. So what we don't know is we don't know what our opposite side is. So can we find that opposite side? Yeah, we've got the Pythagorean theorem. We can do that, okay? So if we want to name this, if we want to give these some letters here, we can say that this is A, we don't know what that is, B could equal 1, and C could equal 2. That way we have things we can plug into the Pythagorean theorem. So A squared plus B squared equals C squared. That's the Pythagorean theorem. We don't know A squared. We're trying to find it. B is 1, so 1 squared equals C squared, which is 2 squared. So this is a pretty easy one to solve here. We get A squared plus 1 equals 4, so A squared equals 3, or A is equal to the square root of 3, because in this previous step here, we're taking the square root of both sides. Okay, so next step then, we've got our missing side now, that's 3. Keep in mind that is our opposite side. So we've got our opposite side, we've got our adjacent side down here, and we have our hypotenuse. We can find our 6 trig ratios here, okay? So that means we should be able to find what sine of theta is. Make that a little bit thicker here. Sine of theta, so from this angle, sine, remember, I'm going to write out our little acronym here, SOHCAHTOA. Sine is opposite over hypotenuse. So opposite side is, we just found that to be square root of 3, and our hypotenuse is 2, so square root of 3 over 2. Then cosine of theta, that is adjacent over hypotenuse, AH, so the adjacent side is 1, and the hypotenuse is 2, so it's just 1/2. And then we have tangent, which is opposite over opposite over adjacent. So our opposite side is square root of 3. That's what we just found here, remember? And our adjacent side is 1, so that's really just square root of 3 if I reduce that. So there's our first 3, but now I want to do all my reciprocal trig ratios. So that means I want to find out what cosecant of theta is, secant of theta is, and cotangent of theta. What are those going to be equal to? And notice you'd think that cosine and cosecant, both cos, would go along with each other, but it turns out sine and cosecant are the ones that are related to each other in terms of reciprocals. So the only one that's obvious is tangent and cotangent go together, but sine and cosine go with kind of their opposite cos. But the rest of this, though, I don't really need the triangle anymore, because remember, these are just reciprocals of sine and cosine and tangent. So once I find sine, cosine, and tangent, the reciprocal ones are pretty easy to find. So I just have to take this here and write it as the reciprocal, 2 over square root of 3. And this is going to be 2 over 1. And this one here is going to be, well, now it's going to be 1 over the square root of 3 if I flip that. Okay, but I've got a little bit of problem here, and it's an easy one to fix, though. 2 over the square root of 3, I can fix that because I'm not supposed to have a square root in the bottom of a fraction. But we fix that just by multiplying the top and the bottom by the square root of 3, and we end up with 2 square root of 3 over 3. Because the square root of 3 times square root of 3 just turns into 3. This one's fine. I don't have to do anything to it. I'll just reduce it to 2. But this one down here, I get the square root of 3 on the bottom also, so I'm going to multiply the top and the bottom by the square root of 3 on that one as well. We end up with, I'll go to green again like I did in the other one, square root of 3 over 3. So those are your 6 trig ratios there. Okay, so that's what it means when it says find all the 6 trig ratios. But remember, all we're doing was taking the side lengths of this right triangle and just writing them as ratios with each other. Pretty simple when it comes down to it. Let's look at another example here. In this one, I want to find missing side lengths, x and y. So I'm given an angle here, 25 degrees, only one angle, and only one side. Okay, and I need to use that to figure out what these two missing sides are. Now, one thing I should note here is this other angle over here, I could actually find that pretty easy because that is whatever 90 degrees minus 25 degrees is, because those two angles need to sum up to 90 degrees since this already is 90 degrees over here. So it's pretty easy to find that if you wanted, it'd be 65 degrees. But let's just go ahead and use the 25 degree angle for this one and work our problem out from there. Okay, so here's the way you do this. So first of all, I'm going to do is figure out what's my opposite and adjacent and all that stuff. So if you look at from the standpoint of 25 degrees, this side over here is the opposite side. Okay, so x is going to be my opposite side. That means 17 is my adjacent side. And of course, my hypotenuse is the long side over there, y. So let's go ahead and try to find the opposite side first, okay? So if I'm dealing with adjacent, I want to find opposite, and I think of my SOHCAHTOA, well, opposite and adjacent, that's this one right here, tangent. Opposite, adjacent, TOA. So that means I can set up a little equation. Tangent of 25 degrees is equal to the opposite side, which is x, divided by the adjacent side, which is 17. So I just made a little equation I can solve. Okay, so x equals, and if I multiply both sides by 17, x is equal to 17 tangent at 25 degrees. And this is something you can get out your calculator and do. Okay, tangent 25 degrees is something you plug into your calculator, but make sure you are in degrees mode. That's super important. So I'm just going to plug that in here, 17 times tangent of 25, and I get, I'll round this to the nearest tenth, about 7.9. So there's my one missing side. But now I need to figure out what is y, my hypotenuse here. So one way to do that could be to use the Pythagorean theorem at this point. Now that I know what x is, and I already have this other side 17, I could plug that into the Pythagorean theorem and figure it out. But let's use another trig ratio to do that. Okay, I'm going to take a look and say, okay, I know what the adjacent side is, and I want to find the hypotenuse. What are we dealing with there? Well, adjacent, hypotenuse, that's AH or cosine. So I'm just going to start by writing a little equation using cosine of 25 degrees and then start filling in the blanks. Adjacent side is 17, hypotenuse is y. So I've got another little equation to solve. And if I want to rearrange this, I need to multiply both sides by y to get rid of that. So that would cancel out here. But then I'd want to divide both sides by cosine of 25 degrees. And basically, the y and the cosine of 25 swap positions. And now I have y equals 17 over cosine of 25 degrees. So another one we can plug into our calculator, 17 divided by cosine of 25. And we get about 18.8. Okay, so you can feel free to try those on your own as well. But that's how you find missing side lengths. Well, or you might be thinking, well, what if we had a missing angle? What if we had two side lengths and we didn't know anything about the angles? Well, turns out there's a way to do that as well. So here's one. Let's find the missing angle x in this case. So we're going from the standpoint of this angle down here. So that means this side over here is the opposite side, and this is the adjacent side. And of course, this is the hypotenuse, but I don't know anything about the hypotenuse. But I do know 9 is the opposite length, 10 is the adjacent length. So opposite, adjacent, let's just write up our SOHCAHTOA up here again. That looks like a tangent situation because of opposite, adjacent, TOA. Let's write a little equation. Tangent of, well, I'm just going to say x. Don't know what it is. And you can put the degree symbol on there if you want, but it's not super important. We just need a variable there. Tangent of x equals opposite, which is 9, over adjacent, which is 10. Now we just have to figure out what is x. Well, it turns out there's a way to undo tangent or sine or cosine, just like multiplication has an inverse operation of division, or addition has an inverse operation of subtraction. Tangent has an inverse operation of inverse tangent. So I can literally solve this for x by taking the inverse tangent of both sides. So this little thing right here, we call this the inverse tangent. Or if it's sine, inverse sine, or sine inverse, some people say. So that little -1 there, this little -1, that doesn't mean raise it to the -1 power. It just means this whole thing means it's the inverse tangent, which is a function. And if you look on your calculator, right above the tangent button, you'll see there's a little tangent to the -1 button. So all you have to do is hit the second button to access that. And again, make sure you're in degrees mode, super important for this. But you literally just plug in this thing as it looks. So second tangent, and then 9 divided by 10. Make sure you put a right parenthesis on that. It's really important that you're taking the inverse tangent of the whole thing. And then we get, I get about 41.98 degrees, or about 42 degrees. 42.0 degrees, okay? Which looks about right. It kind of looks like it'd be a 42 degree angle somewhere in there. So that's how you can find missing angles, using inverse tangents. So to summarize a couple things here, some final thoughts. The hypotenuse is always going to be our longest side, okay? All right, that's always the opposite side. If I draw a little right triangle over here really quick, it's always going to be this long side here, always opposite the right angle there. Always make sure you're in degrees mode when you're on your calculator for these problems. We'll talk about a different one later. Radian's a different unit of measure for angles, but for now we want to make sure we're in degrees mode. You want to treat trig functions just like operations, like adding and subtract, etc. They can be done, they can be undone by the inverse. So sine inverse will undo sine, for example. So if you had this here, sine of theta equals 2/3, you can find what theta is by taking the inverse sine of 2/3, just like we did in that last example. So that's kind of a summary of everything we did in that section, and pretty much the summary of what's going to be on our final exam for the Algebra 2 class here this year, 2020-2021 at Cardinal Mooney.